Hi everyone. So welcome to this live session. Let me see how many people have logged in. Hello. Okay, so let's begin with this session. And I already have some questions. Some of you have already posted those questions. So I will address these questions first, and then I will take more questions as you people type it in. Okay. Um, right. I'll wait for a few minutes as other people are joining in. Okay, let me begin by what I will do is I'll first take care of the non-technical questions, and then we'll take technical questions as they come. Okay. Uh, One of the first questions. This is by Nitish. Nitish, if you're there, say hello. This question is primarily about career advice. I must admit that I'm not a career you know counselor. I can give you some advice based on what the way I have grown in my career, and yeah. So your question is scope of pure science in India compared to engineering in money prospects. That's a difficult question to answer, but the answer is somewhat easier. If you are in engineering, quite obviously the money prospects are better. There's a lot more application. There's industry waiting to employ you. But in physics, of course, the job market is limited. Um, as far as the career is concerned, physics is not a career where uh, you will suffer or something like that. Famously, one of the Professor Arvind Kumar from TIFR, he had once said, if you are in physics, maybe you won't own a Mercedes, but you'll definitely own at least Maruti Suzuki, something like that. So, in that sense, career in physics is pretty good nowadays. Even the academicians draw fairly good salary. So that's about the money prospects. Um, Basically, this question which Nitish is asking is about engineering versus physics. You see, if you are committed to, in fact, one of his questions is about how do I convince my parents to pursue physics rather than engineering. Now, the point is this: if you can talk to your parents and essentially you should be doing what you like. If you like physics, you should be doing physics, and you should be able to convince your parents about that. But if you're not, in case you're already committed to engineering, I think you shouldn't worry too much about it. I know several friends, for example, the very famous astrophysicist from uh, Ayuka. He is my friend, and he is from mechanical engineering background. The people from civil engineering background, they have made a switch to physics after their undergraduate studies, or even some of them have shifted from postgraduate studies. So this is very easily possible as long as uh, you do your math well. You see, the main binding or underlying language of engineering and physics, or pure sciences for that matter, or formal sciences for that matter, is basically the the is basically mathematics. So is basically mathematics. So as long as you do mathematics well, it's possible to switch from engineering to physics without any problem. Now, question of whether we can go from physics to engineering or not, that seems little harder to me. Uh, you can imagine, going back to civil engineering from physics is definitely harder, but the other way around has never been a problem. And I know many people who have done their undergraduate in various subjects and then switched back to physics because they loved physics. And you should do that too if you are already committed to engineering. And that's about all. Yeah. Then the second question is, so second question is from Ruchi. Uh, she says, I'm currently learning MATLAB and wanted to know how much of it is actually used in physics, especially research work. Oh yes, it does. It gets used very, very commonly and very heavily. And I will also advise you to look at other packages like Mathematica, Octave, and so on. See, this is the era of computational work. A lot of work is done where you cannot do analytical and compact calculations. The computational work actually gives us several leads. So computational work is very important, and MATLAB definitely is learning MATLAB definitely is an asset for you. Okay. Then yeah, one more comment Himanshu has made, that the doubts posted on the discussion forum. Yeah, I noticed that the doubts have not been answered very regularly. I'll make sure that they are cleared, and explanations are given on a regular basis. Finally, detailed solution of assignments. Yes, I have already started uploading the solutions. So solutions of first 3 assignments are already on the course page. Fourth one, fifth one is ongoing. So fourth one we will upload soon. What are the best books for numericals for these topics? You see, the level at which we are talking about, the 12th standard, like numericals don't play much role anymore. Yes, numericals are important and one should do those numericals too, but primarily, now we are at a stage where we do a lot of formalism. In fact, this course, when it was run last year, did not have these application topics like rigid bodies or central forces. It was supposed to be entirely a theoretical platform. That's it. Which means we do formalism, and that is it. So there's actually no scope for numericals really speaking in this course. And even in central forces or rigid body dynamics, more than numericals, I would like to talk about ideas and whether uh, you can do those theorems and proofs. So a lot of theoretical work actually gets done. And that's why the name theoretical mechanics. We would not be doing too many numericals, but instead of book for numericals, I can suggest you books for um, solving problems. So the problem at this stage will not be really numericals, but they will be more like prove this, show that kind of algebraic or derivations kind of problems. And we can suggest a lot of books which will contain problems of this kind. Anyway, Goldstein book already contains huge number of problems, so you can look at the Goldstein's book too. But there are of course large number of books. I will post a list in the discussion forum. Okay, I think that's about all about non-technical questions. Okay, so now I'll take technical questions one by one. Uh, okay, this is a question from Savik. He's asking why the functional f does not depend on higher order of derivatives. Okay, higher order derivatives of y. No, of course they can. It depends on the kind of systems that we're talking about. Here, of course, we're talking about generalization of Newtonian system, where the final equation of motion was second order differential equation. And that's why you get Euler-Lagrange equation, which involves 1 d by dt, and then you need to have derivatives of y, uh, first derivative of y. That's it. But if your system, no, whatever system that you're talking about, not necessarily mechanical, but any dynamical system that you're talking about, if it involves equation of motion involves higher orders of derivative, your action functional also will involve derivatives of higher order derivatives of y. Of course, it will do. So it depends on what kind of application we are talking about. So in our mechanical course, this is all we need. How to draw a phase space trajectory for given arbitrary potential. For example, Vx is equal to ax square plus b by x square. But then you have to wait for, I think, 9th week, or will it be 8th week? I think 8th week. In the 8th week, I will talk about the Hamilton's equations. And the moment I talk about Hamilton's equations, the idea of why we introduced phase space would become clear. Okay, and also that will give us an idea of how to draw the phase space diagram, especially for this particular case that you have mentioned here, which is ax square plus b by x square. In that case, of course, the potential doesn't depend on time t, so, and it's probably one-dimensional system. So here the total energy is conserved. So in fact, total energy will be equal to p square by 2m plus v. In which case, you already have an equation. E is equal to constant, which means p square by 2m plus v is equal to constant, is an equation of curve in two-dimensional space, in phase space. So that automatically gives you curves there. Okay. Then the third question from him is, can we apply variational principle even if y is not a smooth function? No, we cannot apply variational principle because it involves the derivatives of functions. Okay, variational derivatives, which means the path must be at least sufficiently differentiable. See, the word smooth in a mathematical sense means all derivatives exist. But that is not necessary. So for our case, we need the first derivative. So at least the first derivative must exist and it must be continuous. Okay, and in that case, you can use the variational principle. But if it is not C1 class, that means if it is not differentiable once, then of course you cannot use the variational principle or the mechanism of variational principle. If we have a system with n particles with k constraints, out of which n are usable, what will be the degree of freedom of the system? Okay, so here the idea is something like this. See, you have to begin with, suppose I have n particles. In that case, I would have 3n coordinates, 3n degrees of freedom. And then this system has certain forces which can be thought of as constraint forces. Once you identify those, you can eliminate degrees of freedom using the constraint equations. Okay. Once you can do that, the resultant system will have number of degrees of freedom reduced. Okay, fine. Now, how many can you reduce? So how many are usable? N are usable. By usable, what you mean is you can actually use those N constraints to eliminate variables, which means I would actually settle down to 3n minus small n. 3 capital N is the total number of particles, 3n is total number of coordinates, n is the number of constraints that we are going to use. Okay, and then it will be 3n, 3 into capital N minus small n. That would be the degree of freedom of the resulting system. And what happens to those? So you have k constraints. So I'm assuming that k is larger than small n. So k minus n constraints are of course there, which will be treated not as constraint forces but as applied forces. Okay, so it's up to you. If you can use a constraint to reduce the complexity of problem by reducing the number of degrees of freedom in the system, that's great. Okay, if you cannot, you have to solve the full problem anyway. So to that extent, degree of freedom would be reduced only if the holonomic constraint usefully reduces the degrees of freedom. Okay? Will chaos be taught in this course? Originally I had planned it, but it seems there is not enough space in 12 weeks. So what I am planning to do is I'm going to add additional lectures to the course, but they will not be part of the syllabus and they will not be listed under the course name, but it will be there in the same playlist. Okay, so I'll add the lectures at the end of the playlist. Okay, so those were the questions from Savik. Now one more question from Ruchi. Okay, how to find degree of freedom of complex systems which have joints, supports and rollers. Okay, this is more of a mechanical problem. If you have a joint, what I'm assuming from your question is you have two rigid sections, and these rigid sections are tied to each other by a joint. Okay, something like that. So each rigid body, of course, has certain number of constraints of their own, but the point of the joint, the coordinates of, so joint belongs to both rigid sections, and the coordinates of the point from one rigid section are exactly equal to coordinates of the joint or that point of joint from the other section. They are equal. So that basically adds, if it is a planar system, then it automatically adds two constraints. Okay, and then your number of degrees of freedom will drop by 2. When you say support, for example, I believe there is one rigid section where support is fixed to some rigid section. It's not like a joint, but there also same thing will happen. The coordinates of the support are fixed, so you get depending on whether it's a planar system or three-dimensional system, 2 or 3 coordinates are fixed in space of one section of your rigid complex system, rigid section of your complex system. Okay, so that way the constraints will work. Basically constraints are obvious that the joint means 2 rigid sections are connected. Question is how to reduce the degrees of freedom using this joint, but that is very obvious. You can ask me a question again if you think I have not given enough explanation. On the question of bead on rotating wire, how do we find the work done by constraint force? For that you need to find out the actual displacement. The virtual displacement will not do. The actual displacement will be needed to be calculated, and in that case, in fact, in the bead on rotating wire is a very interesting problem. So as the bead travels upwards along the hoop, since hoop is rotating, the normal forces are perpendicular to the wire. Okay, they are tangent. So basically, if bead does a circular motion, the normal force will be tangential to the that circular path. And then you have to find out the actual displacement, multiply it by take a dot product with normal force to calculate the actual work. Uh, this is a rather interesting question. I will post a solution in discussion forum. Why don't you ask me this question in a discussion forum? I will post a full solution to this problem. It's rather involved. Okay. One more question from Himanshu. It says, in physics, two laws lead to same results. Is it possible that these two laws have interconnections between them? In our case, we have derived Lagrange's equation from two different principles. So what is the connection between principle of virtual work, that's D'Alembert's principle, and Hamilton's principle? Now, Hamilton's principle basically is designed for what is called as a monogenic system. That means we'll assume that the forces involved, they can be derived from some generalized potential. So those systems are called as monogenic systems. And D'Alembert's principle, in that sense, is more general. It applies to wider variety of systems. So let's look at, so their domain of application is different. But then there is an overlap. So wherever there's an overlap, the D'Alembert's principle can be obtained or can be proven from the Hamilton's principle. Okay, so to that extent, wherever there is a common application area or application in a particular problem where both can be used, they are identical. Okay, and you can prove one from the other. But of course, principle of virtual work does not talk about potential. So that actually has also wide variety of sort of systems where you can apply the D'Alembert's principle. It's also possible to extend Hamilton's principle to some extent by adding Lagrange's multiplier method and so on. And the Lagrange's principle can actually cover, the Hamilton's principle can actually cover larger number of systems, but this is essential difference between the two. Okay, the two principles apply to different set of systems with some overlap between them, and within that overlap, both the principles are sort of equivalent to each other. Then second question that he's asking is, it is said that laws do not have proofs. So one can state Hamilton's principle also doesn't have any proof. So it's also is it also possible that these principles can be derived from more fundamental principles, okay, that come later in time? Or is it possible to prove Hamilton's principle from some sort of a quantum mechanical path integral formalism? First of all, yes, laws do not have proofs. Basically, law is a statement of fact, and it's a statement of observed fact, which also means that observations we have done till now, if they are refuted in future, that law does not hold anymore. Now, assuming that this law has been verified till now, and we haven't found any violations of that law, the law holds. Okay, this is the whole idea. All crows are black is a law, but until we see a white crow, okay, if we manage to find a white crow, the law will not hold anymore. So to that extent, the law cannot be derived, but it has to be only subjected to verification by observation, okay, by experimentation. And whether it can be derived from some more fundamental principle or not, but you look at it this way. In 17th century, Newton gave his laws of equations. They got generalized. the more fundamental principles emerged. Like action principle seems to be more fundamental than the Newton's equations. Then you have relativity coming in, and then you have quantum physics coming in. Laws are continuously modifying. Whenever a law is generalized to a bigger system, we make sure, when we are making newer models, we make sure that our previous models are included inside. So, for example, special theory of relativity. It's now accepted that that's valid theory. But then, as the velocities become very small compared to the speed of light, the entire relativistic mechanics comes down as a limiting case to Newtonian mechanics. So every time a newer observations are done, more violations of existing law are found, we make newer theories, and those newer theories, of course, are supposed to include the previous theories as limiting cases. Okay, so to that extent, yes, it is true. And can you derive Hamilton's principle from quantum mechanical path integral? No, but the Hamilton's principle gets generalized in quantum mechanics. So you see, it's like this. In classical mechanics, what we say is this: you take starting point, end point, and there are infinitely many ways of going from starting point to end point. Now, the classical path is the one where the action is minimum. In quantum mechanics, this gets generalized. In Feynman's idea of path integral formulation of quantum mechanics, you again can go from first initial point to final point in many different paths. But like classical mechanics, it's not deterministic anymore. So the particle or system could take any of these paths with various probabilities. So in quantum mechanics, we in fact, instead of saying that system would take one particular path with 100% certainty, for which the action is supposed to be minimal, in quantum mechanics we say, well, it can take any of these paths, and the probability for this path is this much, and so on. And that transition amplitude or probability amplitude is actually connected to the action. Okay, I will not go into the detail of that, but it goes into the phase of an exponential. So the action does play a role in formulation of quantum mechanics. Then this is a question from Kunal. How do we know that Hamilton's principle will give unique path? No, there's no guarantee. So the question is, how do we know that the Hamilton principle gives us a unique path? Which also translates to, how do we know that there is a unique minimum to the action principle? Instead of Hamilton's principle, I would of course say a variational principle. In general, in a variational principle problem, the minimum is found, but that's not guaranteed to be what is called as a global minimum. What that means is that this may not be the only path where there's a minimum. For example, if you take a system like where the potential function is x square minus a square whole square. Now this has two minima, okay, and when you try to find one minimum, depends on how you approach the point, and depending on that you will hit one of the minima. So in the Hamilton's principle or variational principle, the uniqueness of the path is not guaranteed, okay, and we don't know how to do that. More than that, how do we know? In fact, it's a extremal principle, you see. We don't even know whether it's minimum or maximum. And there is of course way of finding out. Once you have calculated the path, you can now go back and try and find out whether it's a minimum or a maximum by looking at the perturbations. Okay, perturbations about the stationary path. This is exactly what you do when you try to find a minimum of function. You look at the second derivative. Okay, and if the second derivative is negative, then it's a maximum. If it is positive, then you have a minimum. Okay, so that way you have to calculate the second derivative in some sense of the functions, and then you can decide whether it's a minimum or a maximum. And also there is no guarantee that it's a global minimum. Okay, so I hope I haven't missed any of the questions there. Okay, here's a question from Indranil. Indranil is asking, okay, so in central force problem, during converting, basically during finding effective one-dimensional problem, if we take energy conservation perspective, then effective potential will become actual potential plus L square by 2 mr square. Okay, that's the term coming from the centrifugal force. But then he says, from Lagrangian perspective, the effective potential will become actual potential minus the centrifugal term. I will try and explain what he's trying to say. See, when you're talking about energy, it's kinetic energy plus potential energy. Kinetic energy has an angular part. You shift that angular part to the potential. That's when you get a plus sign. So angular part has a plus sign, potential has a plus sign. So effective potential becomes V plus centrifugal term. In Lagrangian, you have T minus V. Now, if you take a angular part from the Lagrangian and shift it to potential to make it into effective potential, now because potential comes with a minus sign, V effective will become V minus L square by 2 mr square. But that's incorrect. Okay, the Lagrangian perspective is incorrect for following reason. It's a function of theta, r theta, r dot theta dot. If you want to get rid of one of the variables from this to construct effective Lagrangian for 1 degree of freedom, that's not the way to do it. You cannot simply take theta dot term and shift it to potential term. That's incorrect way of doing it. The procedure for this is called as a Rauthian procedure, okay, or Raut's procedure. And wait for the Hamiltonian dynamics, which will come in 8th week. In that lecture, I will, or either that lecture or the next lecture to that. But in that week, when we are discussing Hamiltonian dynamics, I will discuss what is called as a Rauthian procedure. So you go from Lagrangian of 2 degrees of freedom to 1 degree of freedom. You have to eliminate 1 degree of freedom, and there's a procedure for doing that. And if you follow that procedure, you get the Lagrangian for 1 degree of freedom. That's when your V effective will again restore that sign to plus. Okay, so there's no discrepancy here. You shouldn't simply take kinetic energy terms from Lagrangian and add them to potential term to create effective potential. That is not correct procedure. And second question here is, why differential cross section is phi independent? That is very easy to see. Remember, our central potential, first of all, is independent of both theta and phi. Okay, so once it is independent of theta and phi, if I didn't have the scattering particle coming in, then the scatterer's potential in fact doesn't depend on neither theta nor phi. Okay, but now what we're going to do in our experiment is we choose the z direction and then we stream the particles along the z direction. So we have broken that symmetry of the system by choosing the velocities. Okay, but at least only one symmetry is in some sense removed, but there's still cylindrical symmetry in the problem. Uh, by that what I mean is this. Suppose you have scatterer and your particle makes an impact parameter towards the positive side or upper side, the trajectory will get, if it is a standard repulsive potential, trajectory will get deflected upwards. If the particle has the same impact parameter on the lower side, the particle will get deflected downwards with the same angle? Of course, yes. And then think of it as, if you keep the impact parameter same, but choose any random phi, the angle phi, z-axis together mark a plane, and your trajectory of the particle will remain in that plane. But in that plane, the amount of deflection which is measured with respect to z-axis, that will be exactly same. So in that sense, the deflection depends on the impact parameter, which is distance from the z-axis, but it doesn't matter what angle the impact parameter makes with the z-axis. Okay. So to that extent, so there's basically still cylindrical symmetry left in the problem, and that's why the differential cross section will be independent of the phi angle. Okay, so these were the questions which I had gotten earlier. Now let me look at some questions which are coming in here right now. Okay. Okay, Kunal, you're asking about books again. Yes, I will give a list in the discussion forum. Okay. Then Mehul. Hello, Mehul. Then I will skip saying hello to everybody by name. Hello, everybody. Okay. Here, Ajil, for a charged particle in the electromagnetic field, why do angular coordinates become cyclic? I mean, the velocity depends only on the radial coordinates. No, Ajil, I did not understand your question. Can you give me more specific about the specific information about the problem that you want me to answer? Because in general, in electromagnetic fields, why would angular coordinates be cyclic? They probably will not, unless you're talking about very specific system. Yeah, Jatin, I just answered this question that V effective, which is V minus L square by 2mr square, that would not be correct procedure. Okay, the correct procedure is to use Rauthian procedure, which I will discuss later in the when I am discussing the Hamiltonian dynamics. The correct sign there would be actual potential plus L square by 2mr square. Okay, somebody named H. The number of degrees of freedom in a rigid body, like the number of constraints is, if we subtract, no. Okay, so his question is about the number of degrees of freedom in rigid body. It's true that if there are n particles in rigid body, there are 3n coordinates, but then there are n into n minus 1 by 2 constraints. But all these constraints are actually not independent. They depend on each other. Depend on each other in following way. Okay, I'll give you one simple example. You take 5 particles. Okay, when we take 5 particles, suppose I have 4 particles. So 3 particles will have 3 constraint equations. When you add fourth particle, you add 3 more constraints because fourth particle's distance from remaining 3. Okay, now you add, so basically now you have a total of 6 constraints. Now when you go and add the fifth particle, now what happens? Number of constraints will become n into n minus 1 by 2, that's actually 10. But look at it this way. The fifth particle's distance from particle 1 to 3 give me 3 constraints. But once I give you these 3 constraints, the location of fifth particle is fixed. And from this information, I already know distance of fourth particle from the first three particle. Now I know distance of fifth particle from first 3 particles. What about distance between fourth and fifth? Oh, I can calculate it from the geometry. Okay, so the distance between fourth and fifth actually is not a new constraint. It can be written in terms of the first 9 constraints that you already have. And in that sense, the 10th constraint is actually a dependent constraint, and hence okay. So basically 3n minus n into n minus 1 by 2 for large n, in fact, will be a very big negative number, which is not correct. That is because n into n minus 1 by 2, even though total number of constraints, they are all interdependent on each other. If you have understood, please let me know in the forum. Okay. A digression. Kunal has a question. How hard is it to get a PhD in best colleges of USA for a decent student? You said we are physicists and we talk about quantifiable entities. A decent student and best college, these are non-quantifiable entities, you see. So to that extent, and in addition, of course, so it depends, even in India, for example, we have different levels of institutes, but generally, my advice to you people would be, since you're talking about PhD, is I'm going to assume that you're already in MS. Okay, so my advice would be, suppose you like a particular topic in physics, say theoretical condensed matter physics. Then you do a little bit of research. You go to particular institute's web page, look at the faculty members' web pages, what kind of work they are doing, where they are publishing, and things like that. What about their collaborations and so on. That gives you an idea of how active a person is, and depending on that, when you're going for PhD, you should look at the faculty members whom you want to join, rather than go by perception of people about the university. For example, you might have 2 universities. One university may have a very good condensed matter department, and the other university may have a very good high energy physics department. Well, you see, you don't have to go by perception. You have to actually, because you are a MSc student, you are in position to do that kind of research and find out which department in this university is better, in the department which topic is more vibrant than the other topics. You have to do that kind of work and find out. So the same thing will apply to US universities too. How hard is it to get a PhD in best colleges of USA? I really have no simple answer to this question. I mean, anything I would say would be simply a, a guesswork on my part, which I will avoid. Hmm? Can I use this type of physics to create some industry work? Uh, this type of physics, by that you mean a theoretical work? Uh, Slightly less likely, but in physics, of course, there are many applied physics areas, and there are, uh, there are many interdisciplinary areas where engineering and physics collaborate with each other. And if you really want to, if want to give you a somewhat casual answer, you look at, uh, there's this movie called, um, I forgot the name of the movie, but it's basically a brainchild of Kip Thorne, who is astrophysicist. So, um, you see, physics is everywhere. It's just a question of how we sort of collaborate with each other. And in fact, if you look at this famous LEGO experiment, it's not, LEGO experiment is not about only physicists, and detecting gravitational wave is a ultimate aim, but the large number of engineers would be working there, enormously large number of there are many aspects of experimentation which require engineers and physicists to work together. Yes, but whether industry kind of work, yes, not the theoretical mechanics that we are talking about, but there are areas in physics, and especially in optics, for example, electronics and so on. They have interface with industry. Especially if you talk about modern, very large scale integrated chips, the size of transistors have dropped down to 10 nanometers, and now it's coming very close to each transistor being it's just like few atoms, where quantum effects become very realistic possibility, and you have to really worry about it. So that the physicists and engineers would be working together to get the industrial output. Yeah, but especially my own specialization is very theoretical, and I do not collaborate with industry, but I know there are a large number of people who do. Indranil is asking, can you give some insight in the ways a physics postgraduate can pursue research work? Primarily, it's about taking PhD positions in various institutes. Uh, those days of Einstein are gone these days. I mean, uh, the state at which uh, current physics is, it would be very difficult for you to be doing research, uh, cutting edge, research on the forefront, without having an affiliation with an university and having collaboration with people. Or probably you may still be in teaching in some college or university, and maybe collaborating with some people in other institutes to pursue your research. But that basically is the idea. The large number of, so we in IIT, for example, have a something called as a QIP program, where the teachers who are basically postgraduates, and they're teaching in colleges, but then we give them opportunity to join a PhD program as a part-time program, and they can pursue their PhD work, which is basically pursuing the research work. So yes, these are the ways in which you can Jatin has asked a question saying that please give 10-15 good problems. Solving all problems from a book is not always possible, so it will help. What I can do is this. See, typically, because I have to give MCQ kind of questions. The questions that I have given in assignments, they do not fully cover the entire range of problems that we need to solve at this stage. Uh, so I can of course here when I teach course in IIT, I give them assignments where there are many long problems. I can share my assignments with you people and the solutions of those. You can try those problems for yourself and then cross check with the solutions that you can do. Yeah, so I will definitely do that. If a molecule has, so this is a question from H, if a molecule has n atoms, then vibrational degrees of freedom is 3n minus 5 or 3n minus 6. 3 translational degrees of freedom, 5 or 6 rotational degrees of freedom, whether the molecule is linear or non-linear. I not immediately clear of what you are asking, but if you wait for 1 week, I will. I'm going to anyway do this vibrational motion in coming week. As soon as the rigid bodies are over, we will do basically vibrational studies. So if you wait for that, or you can post more detailed question. Oh, I see. I guess what you're trying to say is this. If this was a rigid system, then okay. So 3 translational degrees of freedom and 3 rotational degrees of freedom. Rotational degrees of freedom would be 3, of course. And then the remaining degrees of freedom now, because the system is not rigid, is basically 3n minus 6. Is that what you're trying to say? Just give me one moment. Excuse me. These questions are available to everybody, right? The chat. Okay. Yeah. So I think that is what you're talking about. In that case, it will be correct. So when you of course have a system, when do we classify degrees of freedom as translational, rotational and vibrational ones? When you have a system where there must be at least some part of which can be thought of as a rotation and something that can be thought of as a vibration. If you just have 3n minus 1 particles which can move about, they can have any energy scale and move about everywhere, then of course there is no sense of talking about what is called as a rotational degree of freedom or vibrational degree of freedom. So typically, when you have uh, a system like this where you want to distinguish between translational and vibrational degrees of freedom, the system must have some characteristics to begin with. First of all, there must be an equilibrium. Okay, once you have equilibrium, which is close to how we would perceive that as a rigid system, and then once you have that rigid system, the small deviations from the equilibrium position can be thought of as vibrational or perturbational degrees of freedom. But otherwise, depending on the system, we will have to make those distinctions. At some point, the distinction will not be straightforward. Hmm? I will discuss this question when we come to a chapter on oscillations. Wait. Yeah, here it is. Okay, so Mimansha, yes, I will write a list of books. Okay, here's the question which debates goes on all the time, and which is what why I answered sometime earlier. Which principle is more general principle, D'Alembert's principle or Hamilton's principle? Depends on the kind of systems that you're talking about. Hmm? They both address different kinds of systems, and you see, to let me put this in perspective. Uh, in the perspective of a physicist, in the perspective of a physicist, I really don't want to solve this, standard mechanical engineering problems. I'm more interested in the world as a whole, universe as a whole. And if you look at, for example, these contact forces, spring forces, or friction, they all actually are manifestation of the four fundamental forces which we know. So, in fact, to that extent, I really would like to keep myself limited to when I'm describing a fundamental theory of universe to the four fundamental forces and see if I can put them in my Hamilton's principle. And to that extent, Hamilton's principle works, and that's what we use to generalize from the Newtonian mechanics or classical mechanics. When we go over to relativistic mechanics, when you go over to quantum mechanics, that remains our guiding principle. Okay, and we generalize that principle in physics. We don't generalize D'Alembert's principle, because D'Alembert's principle, even though it addresses many more problems of your daily nature, the problems of your car, what drives your car and so on, your mechanical machines, which are not covered by Hamilton's principle, but in a more fundamental sense, Hamiltonian principle will always remain the most general principle. Okay, from physicist perspective. Same thing, you go and ask the mechanical engineer, he would say, okay, let me look at how many kind of systems that this principle applies to. And then in that case, he would argue that D'Alembert's principle is more general. But essentially, these two principles are addressing completely different, not completely different, but different set of problems there. Sir, I was not able to complete 3 of my assignments. Can I still give exams? Please, uh, these kind of questions, I think you should ask uh, Siddharth. This is in reply to your question. Uh, about the assignment submission and exams, please write to the NPTEL administrators, because I'm not in position to answer that question. Then Rushi, all I ask is, can you include more application-based study, maybe little more longer lecture with an important application of particular idea being discussed? Uh, yes, I will keep that in mind. Typically, the course was designed to be very theoretical in nature to begin with. That's why the name also, I did not name the course as classical mechanics like a normal textbook is named, but called it as theoretical mechanics because the focus was only on formalisms rather than on applications to begin with. Yeah. But yes, I will keep that in mind. Sure. Yeah, good morning to everybody. Um, for central forces, motion is planar. Why is that symmetry about theta and phi gives conservation? Look at it other way around. It's a problem in 3 dimensions. It's a problem in 3 dimensions, and you have this rotational symmetry. Okay? The consequence of this rotational symmetry which is conservation of angular momentum, automatically gives the motion to be planar. It's not the other way around. It's not the motion is planar and angular momentum is conserved. No, it's angular momentum that is conserved. Consequence of conservation of angular momentum is the planar motion. Can we apply Hamilton's principle in case when the energy of the system is not conserved? Yes. The example would be the bead on the rotating hoop. In that example, the energy is not conserved. In fact, in the Hamilton's principle, we came to one important conservation theorem. If the Lagrangian is independent of time, then the energy function is conserved, but otherwise it is not conserved. Okay, so in general, in the Lagrangian, if it has a time explicitly embedded into the expression of Lagrangian, then of course this will not happen. The energy will not be conserved. Mimamsha, yes, we are in. I have already uploaded 3 assignment solutions. We'll do remaining one. When can we expect the next live session? I don't know the schedule, but I think it will be next month, the next live session. Should anyone pursue NET GATE exam even after 1 or 2 years of break after postgraduate studies? Oh yes, of course. See, when you think of it like this, when you come to PhD work, you're still a student in the sense you're learning, but it's already you've finished something like 23, 24 years of your life, and you're ready to get and take the familial responsibilities and your other responsibilities, and that's why the PhD is usually has a assistantship or honorarium or scholarship associated with it. And these days this scholarship is quite handsome in that sense. If you want to commit to 5 years of PhD work or 5 to 6 years of PhD work, you need scholarship, and the way to get this scholarship is NET and GET. Okay, there are very few scholarships other than NET and GET which will give you monetary support when you're doing PhD. So yes, in fact I would suggest, in case you have given NET and GET, you don't have enough score, please do attempt it again and try to get better score so that you get a better institute. Okay, sure. Is there any course for mathematical physics at NPTEL? I really don't know. We need to check. I know there is a computational physics course which is taken by my friend, but whether there's a mathematical physics course or not, I don't know. Will the course, for example, quantum mechanics be repeated in future? That also I have no idea. I think it will be repeated because this is one of the very important courses in the bag of NPTEL. How the velocity and position are taken to be independent variables? Is that just a mathematical contradiction? No, of course not. Okay, so this question, Himanshu, how velocity and position are taken to be independent variables, underlies the entire discussion on the or the entire Lagrangian mechanics is built on the top of that. So if I give you position as a function of time, then you can always calculate velocities for the trajectory of that particular system. Now we want to extend this idea. Think of a space with all possible velocities and all possible positions, and then ask a question. Now what kind of trajectories I can get? Or in other words, let me give you this example. Suppose, uh, okay, just a sec. Can I write now? I'll write here. Hopefully, it'll help. I haven't got that yet. Yeah. Okay. So think of, this is a two-dimensional plane, and in this two-dimensional plane, I give you a trajectory. Okay, and this is a space. So this is your x direction, and this is your y direction. Okay, this is your y direction. Now you have a trajectory here. You have a trajectory here, and then you take a point here. Okay, let me draw a point here. Okay, there's a point there. Now a particle passes through this point. Now it passes through this point. What would be its velocity vector? That would be this. Now I am going to make a slight difference. How about particle goes through the same point but goes a little faster? The velocity will be larger. See? Through a point, the particle can pass with any arbitrary velocity, which means the Lagrangian can be function of not just the position but velocity too. So in that sense, velocity and position are taken as independent variables, and when you of course solve the problem, you get the trajectory of the system based on the initial points, then the velocities and position are connected across on the trajectory. Yeah, can you go back to the Sujit is asking a question about PhD on theoretical physics. How hard is it? Well, it all depends on your mathematical preparation. Remember, theoretical physics would, of course, use fairly advanced mathematics. And if you are prepared with your mathematics, or if you are willing to prepare yourself with required mathematics, see, physics basically is few ideas and a lot of mathematical work. Okay, so in that sense, it would not be hard if you're prepared in maths. That's a simple answer I can give you. If you find abstract math hard, you'll find theoretical physics hard. Time is over. Okay, so we need to wind up soon. So I will answer a few more questions before I wind up. 2-3 minutes. Yeah. So, so whether we prefer theory or experimental research for PhD entirely depends on you, your aptitude. Okay, not just physics. Whenever I come across a student and he asks me a question like this, whether I should do physics or chemistry, well, the answer lies within you. You need to find out what you like more and do that. Thank you, Indranil, for nice words. Ruchi too. Can you take one-dimensional example with time on one axis to prove the same? Okay, Himanshu, I will now, I need to wind up this session because there's another session going to start after this. So what I will suggest is, why don't you post this question on the discussion forum, and we'll continue discussion there. There we can go back and forth and have a discussion on this topic. Okay, so that is all. Great to have met you all in some sense in person. So I'll see you next month again in another live session. Okay, bye for now.